All right, I had a couple of questions. One about electrolytic cells. So you have different types of electrolytic cells. You have the one-pod electrolytic cell or the two-pod. This would be a one pot or one beaker. This liquid sodium chloride goes and contacts both the cathode and the anode at the same time in the same container. And so this would be like a one beaker. You just stick two electrodes in there. The cathode goes all the way around. The anode just sticks up through the center here. Sodium chloride can go on both sides. And so if you're electrolyzing molten sodium chloride, you're going to produce sodium metal and chlorine gas. And so this is down cell. This is in chapter 21.
So if we had to draw one, could we draw it either way?
Yeah, except you need a salt bridge, and what would you use for a salt bridge here? If you have a two beaker setup, you need a salt bridge. This is kind of interesting because there's a series of redox and acid base and metathesis reactions. Take a look at another cell. As you continue on in chemistry, you'll notice there's some weird bonding features that come about in MO theory. One of these is this, BeCl2 solid. BeCl2 solid. When you try to draw out the Lewis structures, you can't unless the chlorines form a bridging link like oxygen. So this is really weird because you wouldn't expect chlorine to form two bonds in this fashion. Normally chlorine only forms one bond, or in like perchlorate or chlorate or chloride, it could form bonds to oxygen, which are more electronegative with atoms than chlorine. But here, do you see this? And so it's very strange, the bonding here. And so one of these bonds is your normal bond. The other bond is like when you see a bond like this, it's a Lewis base, Lewis acid type bond. Both electrons are being donated by chlorine to beryllium. If I were to ask you to draw an electrolytic cell for the electrolysis of magnesium chloride, you'd just draw it in a beaker. And so you would draw something like this, where you stick one electrode here, another electrode here. You have magnesium ions and chloride ions in the molten state. It would be MgCl2 liquid. And then you put your power supply here. In this case, what would you generate here? This would be the anode of the electrolytic cell, right? So what would you generate at the anode of the electrolytic cell? Chlorine gas. And at the cathode? Magnesium solid. And so, no, not magnesium solid, magnesium liquid. And so a magnesium liquid would float on the surface of this, so you need a barrier here to prevent the liquid magnesium from coming into contact with the chlorine gas.
Why is it liquid and not solid?
Because magnesium has a very low melting point, and magnesium chloride has a much higher melting point. so it's going to be molten. And then you notice this, if you look at this electrode, it's encased. So they put this electrode with a container around it. You know, the molten magnesium chloride can still get up in here, but as the chlorine bubbles out, it's going to be trapped by this tube. So it won't mix with the magnesium metal. So this would be a one beaker type apparatus generating magnesium metal, which is very reactive. Similar situation would be like magnesium chloride AQ. You know, a magnesium chloride AQ though, you might not generate magnesium metal. You know, it depends on the reduction potential for magnesium versus the reduction potential for what? What might interfere if you're looking at magnesium chloride AQ, water. Check out this molecule here. This is a B2H6. If you were to try to draw the Lewis structure of B2H6, what would you come out with? You wouldn't come out with anything that looks right. And so what looks very odd about this? The hydrogen, normally hydrogen forms only one bond, but in this species it forms two bonds, which is very bizarre, isn't it? And so when we're trying to visualize something like this, you know, we really got to get into maybe not our usual. This is more valence bond type picture things, but we really have to get into molecular orbital theory. And so this molecule can be generated in MO theory using quantum mechanics. This would be the electrostatic potential map of this molecule. Very interesting, bizarre species. As for boron, you know, boron has some interesting chemistry. Boron likes to form these cages. You know, this is a very weird cage because what's linking this cage together are hydrogen atoms, isn't it? You know, but a lot of these boron cages link together with carbon or nitrogen atoms. And so I don't think this is very stable here. But it is a very bizarre molecule, isn't it? There's a professor at UCLA, his Hawthorne. His license plate on his car read Mr. Boron, because he was really into boron. He made a lot of these cages. What he'd do is, his research spanned a whole bunch of different things, but one of the things he was into was trying to encapsulate, encapsulate like certain isotopes that are like deadly to cancer cells, and then he would put groups on the cage so that they would be more attracted to cancer cells versus healthy cells. And then when these attach in significant number to the cancer cells, you know, it's easy to break the bonds. You can break the bonds with visible light. And so shine visible light on it, the cage opens up, releases the radioactive isotope or whatever stuck in there, hopefully kill the cell. Boron's also, so we're going to read about boron in the next chapter. You know, boron is a good absorber. You know, boron's good at absorbing neutrons. Boron is good at absorbing neutrons. So we'll take a look at that. Neutrons are pretty deadly. Here's another interesting molecule here, the BF3. You look at that, look at how You know, normally we would think fluorine would be hybridized in what state here? You know, boron would be sp3. Fluorine should be. I'm sorry, boron should be sp2, right? Trigonoplanar. Fluorine should be sp3. It should be sp3, but if you look at this, are the fluorines sp3 hybridized? No, these fluorines are sp2 hybridized. Can you think of a reason for that? One of the reasons is to delocalize the electron density. You know, if the fluorines are sp3 hybridized, then the lone pairs are going to be localized on the fluorine. But by going to sp2 hybridization here, it can help stabilize this, especially with the boron. The boron's quite electropositive. You know, it has less than an octet, so it wants electron density. And so all this can help stabilize that. And so sometimes you see hybridizations that don't look right, you know, because you learn the simple rule. You know, it depends on how many groups you have on that atom. That's why you hybridize it. But it's to help delocalize the electron density through the structure. When you see exceptions to that. Here's another example. This would be a one-pot electrolytic cell. You know, normally if you have molten sodium chloride, nothing's going to happen. You just have sodium ions, chloride ions, or if you have molten magnesium chloride, nothing's going to happen. Same thing with this. Molten aluminum oxide, though, you know, aluminum oxide has, did I talk about this yesterday? No? Aluminum oxide is extremely hard to melt. Why? Actually, aluminum oxide is the wonder ceramic because you know, it's really unreactive. They use it for many different things. You know, they make like cookware out of it for chemists. You know, little pots and dishes and other stuff, so you can cook your reactions. Very high temperatures. Aluminum oxide doesn't really react with much of anything. It has a very, very stable lattice. Single crystals of aluminum oxide are totally colorless and extremely tough. And so they use these for like, they have these single crystal aluminum oxide goggles for like nuclear bomber pilots. You know? And then they dope it. They dope it with something where, you know, it's totally transparent, you can see through, but if there's an electrical signal, it blocks all light completely. And so it's used for so many different things, and also things that you don't expect. You know, gemstones. A lot of gemstones are just made out of aluminum oxide with a little bit of transition metals doped in there. So at the beginning of chapter 24, you see some of those, like ruby, you know, and a whole bunch of others are just either aluminum oxide or a mix of silicon oxide and aluminum oxide. And people make them all the time. You know, they just dope, called alumina. But anyway, aluminum oxide is near impossible to melt. In fact, the melting point of aluminum oxide is way higher than 1600 degrees C. How are you going to melt this stuff? You throw it in a gas furnace and it doesn't melt. You know, that's why they make these boats. If you threw in a metal pot into a gas furnace, it melts into cooled the liquid metal. And so, how do you melt it? Well, you don't melt it. So how do they get aluminum? Bauxite's aluminum oxide. And so do you know how liquid aluminum or pure aluminum is produced? They don't melt the aluminum oxide. They dissolve it in a solvent that's more polar than water. Aluminum oxide won't dissolve in water because water is not polar enough. So can you think of a solvent that's more polar than water? You know what's a solvent that's more polar than water? A molten salt. Molten salts are going to have full charges rather than partial charges. Water only has a delta plus and a delta minus, a partial charge. But if you take a molten salt, it's got a full positive charge from the cation and a full negative charge from the anion. And so something like liquid cryolite can dissolve aluminum oxide. Liquid cryolite's not so hard to melt. A lot easier to melt. So you get that molten and then put this in. Then you can electrolyze it and form liquid aluminum. Aluminum is less dense, so actually not less dense, more dense than cryolite and bauxite, so it sinks at the bottom here. Drain it off. So this is one pot deal.
What is aqueous salt?
Aqueous salt would not work. This is another bizarre structure, Al2Cl6. Okay. All right, so those are some one-pot deals.
What chapters?
This is chapter 20.
Right.
But what I just showed you was chapter 21. You're not responsible for chapter 21.
Okay.
Chapter 21 is just looking at properties of certain elements. In this two-pot deal, this is recharging a battery. And so, you know, in electrolysis, you're either going to have a one-beaker setup or a two-beaker setup. And it depends. Like, a one-beaker setup would just be like sodium chloride. You're trying to electrolyze sodium chloride, so you don't have to separate things because there's no spontaneous reaction. Here, we separate things because there is a spontaneous reaction. The spontaneous reaction should be from left to right. But we're trying to make this go in the non-spontaneous direction, so we have to stop the electrons from flowing and force them backwards. You know, when a battery goes dead, the voltage need not be 0 volts, right? When a battery goes dead, typically I just threw away a whole bunch of 9-volt batteries. The voltage was like 8, in the low 8s. So by the time it gets to the low 8s, it can't power it anymore. So just toss it. That's it. Threw a whole bunch of AA batteries out. They were at anywhere from 1.1 to 1.3 volts. I just tossed them because they're pretty much dead. And so, you know, if I wanted to try to recharge it, you don't try to recharge those primary ones because the reactions aren't so reversible. And if you try to recharge them, they're going to get extremely hot, right? And you're going to get side reactions and possibly gases form. If gases form in that canister, you can have a little explosion. So you might have had. Right, but anyway, we can recharge this one. This is normally trying to go left to right, right? And so this is a 2-beaker electrolysis setup. We're just trying to reverse a voltaic cell. In the one-pot setup, you know, in this one-pot setup, magnesium and chloride, there's no voltaic cell there. It's just magnesium ions and chloride ions. We're not going to do anything. All right. Then the other question is, you know, how do you determine the moles of electrons? I don't know if on this test I gave you an easy one or a hard one. I think I gave an easy one on the practice test. I think I looked at it and I thought, that's too easy. So I've given much harder ones. In the past, it's why. Lots of people get it, so I know it's not too hard. like something like number 3. How many moles of electrons are transferred in a reaction like number 3? That's a hard one. Or it might not be so hard. Six moles is what you got? All right, let's take a look here at, for example, platinum. Platinum is going from 0 to plus 2. We have 3 of them. And so 3 times plus 2 is, each platinum is losing 2. 3 of them, we're losing 6 electrons altogether. 6 moles of electrons. Does everybody see that? You have to watch out, though, because chloride, what's happening to chloride? Nothing. And the nitrates, this is going from plus 5 to plus 2. So each nitrogen is gaining plus 5 to plus 2, is gaining 3 times 2 is 6. So it's 6. Actually, this is medium difficulty. It's medium difficulty because you don't have multiple. Remember when back in chapter 5, when you had like disproportionation reactions? Do you guys remember that? It's when you have multiple things being the oxidizing or multiple things being the reducing agent. It's not just one species. If you only have one species, the oxidizing, then it's easy, right? But if you have 2 species, what tends to happen is people just look at one and count the electrons based on one of those and ignore the other one. And so that's
So you count how many
less
electrons?
difficult.
So are we going to have medium difficulty?
So you count how many electrons were being transferred?
Can you do one more, Professor?
Let's do one more. Let's see if I have a good multiple one here. Take out. This one is still medium difficulty, but at least it's a little bit more complicated. How many moles of electrons are transferred in this reaction? Did I assign this one as homework? 75? No. So we got to figure out how many moles of electrons are transferred.
How do you?
Yeah, this top one.
1.
1? 1? All right. Well, the way you do it is you just look here. Vanadium plus 2 goes to plus 3, so it lost 1. And then this is vanadium in the plus 4, and it goes to plus 3. It gained 1. And so 1 is correct. Okay. I'm about to give up. Which means you'll likely have a easy to moderate one. Unless I can find one quickly in chapter 5.
Gus, are you recording?
Yeah. I know there is one in chapter 5 because it's a favorite. But it's been a while, so. Remember. Well, unfortunately, these aren't balanced, so I'd have to balance it first. But take a look at these. This is what I mean by tricky. Because here, okay, chlorine's no problem, right? Why is chlorine no problem? Because it only ends up in one product. But nitrogen is a problem because nitrogen ends up in two things. And so this could be a case where, one of the nitrogens, we might have like two ammonias. One of the nitrogens acts as a reducer. The other nitrogen acts as a potential. Or both nitrogens act as a reducer, but they don't get oxidized to the same level. They get oxidized to two different levels. And so that makes it more complicated because you could be tricked. This one's easy though because one of the nitrogens nothing happens to, the other nitrogen something happens to. And so there is a reaction that I like with lead in it. That's tricky, that people often get wrong because of that. They don't look at lead doing two different things. But I wouldn't worry too much about it at all. So I haven't been in the mood for put that on there. So just a basic problem. You look at the oxidation states and you see how the oxidation states and that's it. This is okay. In the other direction, this might get people. If I were to reverse this reaction, throw people off, potentially. All right. Does that answer your question, Omar? What other questions do you guys have? Nothing?
Yeah. Well, an electron is jumping from the valence band to the reduction band.
Uh-huh.
The reduction band is anti-bonding particles, right?
Yeah.
So are bonds actually being broken?
Well, normally when you think about it, the more electrons you have in the anti-bonding, it's going to destabilize the molecule. Because the way you think about, a bond in MO theory is different than the way you might think about a bond typically. In MO theory, how do you describe what a bond actually is? Because normally we think, okay, 2 electrons shared is a single bond, 4 electrons shared is a double bond, right? But in MO theory, the way you describe a bond is what? Not overlapping of the orbitals.
It's bond order.
It's bond order based on what? It's based on how much electron density you have in bonding orbitals versus how much electron density you have in antibonding. So if you have, like, say, 6 electrons worth of density in bonding and 4 electrons worth in antibonding, right? then would you say that, 6 electrons makes a triple bond, and then you have the 4 anti-bonding, so you break 2 of those bonds, and you're left with a single bond, right? A bond order of 1. But that's not exactly correct, because what it is just balancing out the interactions, the attractive versus the repulsive. And so what we say for MO theories is we have more electron density in the bonding than the anti-bonding, which results in a net bonding interaction. And so what's going to happen is that an electron goes into anti-bonding, it's going to weaken the bonding interaction. It doesn't necessarily break. The bonding interaction is still there. It's just going to be weaker. I guess in one sense it could be thought of as broken. It's just what we're thinking, as far as a bond goes in MO theory. It's not necessarily an overlap or this. It's just having more density in one place than the other. If that makes sense. All right. Anything else in chapter 21? 20? All right, let's take a look at some crystal field theory questions here. When you look at these questions, let's see how difficult they are. Describe how the crystal field theory explains the fact that so many transition metal compounds are colored. Does someone want to tackle that one? It's not the ligand. The color originates in 2 different ways. One from the central metal, and another from the ligand. The ligand is a different mechanism for color. And the ligand, when we look at the MOs of the ligand itself, there could be transitions, electronic transitions in the MOs of the ligands themselves. But we're just looking at the central metal because we aren't looking at the MOs for the ligands. In fact, in crystal field theory, you don't even look at the orbitals of ligands. You just look at the ligands as being negative charge density. If you really want to look at the orbitals and the ligands themselves, you would have to use what theory? Crystal field theory approximates the ligands as being negative charge density, point charges. You have to use ligand field theory. So does somebody have a good answer for this one? What causes the color? Electronic transitions. Electronic transitions between what levels? Colors are caused by electronic transitions, typically, right? Electronic transitions occur in the visible region of the spectrum. Between what levels? Well, let me just verbally say that it seems like you focused on the previous chapter. Describe how, well, crystal field, as ligands come in, it splits the d orbitals into 2 or more energy levels. And the splitting between those is in the visible region of the spectrum. So when you promote an electron from one lower energy d orbitals to the higher energy d orbitals, you absorb visible light, resulting in color. Do you guys know the splitting patterns? This is octahedral. This is what we call weak field. This would be a stronger field because the splitting gets bigger. Tetrahedral, they're all weak fields, and the splitting is not so big, but it's a pattern like this. This is tetrahedral, right? Square planar is a low spin. The splitting is kind of big, no matter what the ligand. That's square planar. And that results in, visible transitions, or visible light being absorbed and causing these transitions, electron transitions. And so that's what we talked about earlier. 18 cyanocomplexes of transition metal ions, such as iron 2 and copper 2, are often yellow, whereas aqua complexes are often green or blue. Explain the basis for this difference in color. And so they're saying cyanocomplexes are typically yellow, or often yellow, whereas aqua complexes are green or blue. Somebody tackle that one for me.
The cyanocomplexes have carbon in them. Carbon is typically one of the...
Cyanocomplexes are, carbon donors. What do you know about carbon donors? Yeah, good. And so cyanocomplex is a strong field. And so they're going to absorb what wavelength of light?
Low wave.
Short wavelength, short wavelength is high energy. So absorbs high energy, it appears low energy. Whereas aqua complexes are lower field or weaker field ligands, which means they absorb lower energies of light, which make them appear higher energy. Okay. So this is just review of what we talked about. Maybe I shouldn't review it. Should I do wait till you had time to review the notes? Yeah? Or continue? Wait until you've had more time to review this? Continue. And so this is kind of a repeat. If the ion cobalt-2 is linked with strong field ligands to produce an octahedral complex, so which splitting pattern are we looking at? First one or second one? The complex has one unpaired electron. Oh, that's good. I have one unpaired electron there. I don't know how many paired. How many d electrons does cobalt-2 have? This is what I showed in Chem 1A. 1, 2, d7. 7 d electrons. So actually, let's fill this in. 1, 2, 3, 4, 5, 6. The unpaired electron is up here, not down there. This is low spin. Low spin means fill these orbitals first before popping up to here. High spin means fill up here before completing down here. The complex has one unpaired. If cobalt-2 plus is linked with weak field ligands, the complex has 3 unpaired electrons. How do you account for this difference? Well, if it has weak field, then we have 1, 2, 3, and the fourth one would have to go where? Up, because we say that the pairing energy is greater than the splitting energy. Splitting energy is delta. Pairing energy we call P. Over here, the splitting energy is greater than the pairing energy. And so it's 1, 2, 3, 4, 5, 6, 7, 3 unpaired electrons. So that's how we do it. 20, in contrast to the case of cobalt-2 considered in exercise 19, no matter what ligand is linked to nickel-2 to form an octahedral complex, the complex always has 2 unpaired electrons. Explain this fact. Well, let's see. Nickel-2 has how many d electrons? D8. So let's go ahead and do that. So 2, 4, 6, 7, 8. It's 2 unpaired electron. 2, 4. Okay, so we filled that. We're going to fill this. 2, 4, 6, 7, 8. And so we get the same pattern no matter what the ligand because of the number of electrons. #21. Predict which of the complex ions, hexachloromolybdate 3 and tris ethylene diamine cobalt 3 is diamagnetic and which is paramagnetic. And so the first complex is octahedral, right? MoCl6. And so what is the charge on molybdenum? Three plus. How many d electrons does it have? 1, 2, 3. 3. And so molybdenum 3 plus is D3. 1, 2, 3. It doesn't matter if it's strong field or weak field, we're going to get the same pattern. Then we go to cobalt, trisethylene diamine cobalt. What's the charge on cobalt? 3 plus. How many d electrons is that? 6, d6. Are there any s electrons? 4s2? No. And so d6, strong field or weak field? It's strong field. Ethylene diamine is a nitrogen donor, which should be a strong field. d6. And so that's going to tell me how it fills. So I get 6 d electrons. Is it octahedral? Wait a minute. Is it octahedral? Yes, it is octahedral. Why? Octahedral means 6, doesn't it? I only have 3. How can it be octahedral? Because each ethylene diamine is bidentate. So, strong field, octahedral, 1, 2, 3. Promoter pair. Pair, because delta's big. So which one's diamagnetic? Cobalt 3. In fact, we didn't even have to do this because molybdenum 3 plus is an odd number of electrons. If you have an odd number of electrons, it's always going to be paramagnetic. And so this one, we could have saved time because you didn't need crystal field theory to tell you that. The number of unpaired electrons expected for tetrahedral complex, tetrachlorocobaltate, what? Tetrachlorocobaltate. Tell me what the charge on cobalt is. Yes, +2, good. Tetrahedral, what's the splitting pattern? It's just the octahedral upside down. And it's always a small delta. It's about, 4/9 the size of, it is 4/9. 4/9 is actually calculated based on the geometry of that. And so it should be 4/9 the field of an octahedral. About 1/2 the field of an octahedral. And so chloro, it doesn't matter if it's strong field or weak field ligands, they're always going to be a small delta, and there's always going to be a small delta in tetrahedral complexes. And so we got cobalt 2 plus. Cobalt 2 plus has how many d electrons? 7. So what's the question? The number of unpaired electrons. 1, 2. Small delta means these are high spin. High spin means promote the spins up. High spin. 5, 6, 7. How many? 3 unpaired electrons. We might as well finish all these. think I assigned all. Predict whether the square planar complex of this tetrapyridine copper 2 is diamagnetic or paramagnetic. Okay. Tetrapyridine copper 2. You know, it's square planar. Square planar is going to have this pattern: 1, 2, 3, 4, 5. Copper is what charge in this? 2 plus, which means it has how many d electrons? D9. Well, there's your answer right now. D9 is paramagnetic. Yeah, it's impossible this is diamagnetic. You can't form pairs with an odd number. But anyway, 1, 2, 3, 4, 5, 6, 7, 8, 9. You know, we'll talk about nickel in a minute. B, whether octahedral tetracyano manganate 3 ion or tetrahedral tetrachloro ferrate 3 has the greater number of unpaired electrons. So let's first one is manganese. What was the charge on the manganese? Manganese 3 plus, and this is a octahedral complex. 1, 2, 3. And is it strong or weak? Strong. Cyanide is very strong. The ranking goes carbon donors: cyanide, carbon monoxide, followed by nitrogen donors, followed by oxygen donors, followed by halides. Manganese 3 plus is 1, 2, 3 is D4. 1, 2, 3, 4. Big jump. Okay, the next complex is iron, and it's going to be tetrahedral. Iron, what's 3 plus? So tetrahedral. Doesn't matter what the ligand is, but this is a weak field ligand anyway. So iron 3 is what? D5. 1, 2, 3, 4, 5. So iron 3 plus has more unpaired electrons. In example 24.5, we chose between a tetrahedral and square planar structure for nickel based on magnetic properties. Actually, we can predict it without magnetic properties. What do you think tetracyanonickelate will be? Tetracyanonickelate 2 will be tetrahedral or square planar. You know, normally, if you think about nickel, how many valence electrons does nickel have? Nickel 2 plus. How many valence electrons does nickel 2 plus have? 0. Right, and so the bonding is going to come from the bonding to the cyanides. So if we have 4 cyanides, what should the structure be? We got 4 bonded atoms. 4 bonded atoms, Vesper tells you it should be tetrahedral. Right? But does Vesper work for complexes? No, Vesper fails for complexes. And so how can we predict this? We expect it to be tetrahedral, but could it also be square planar? That is, just form a flat square planar shape. And the answer comes from, you know what the answer comes from? crystal field theory. Tetrahedral is 2, 3, right? Square planar is 1, 2, 3, 4, 5. Nickel 2 plus has how many d electrons? D8. So let's fill it. 1, 2, all tetrahedral are high spin. 3, 4, 5, 6, 7, 8. How many unpaired electrons? 2. Over here, if it's square planar, we get this. 1, 2, 3, 4, and then jump 5, 6, 7, 8. Square planar are always low spin. How many unpaired electrons? 0. And so is it a question between paramagnetic or diamagnetic? No, it's a question between energy. If I were to average the energies for all the electrons here, I have 1, 2, 3, 4 higher energy electrons and 4 lower energy electrons, and they'd average somewhere around here, right? If I were to average the energies here, I have 6 lower energy electrons and 2 higher energy electrons. Or in other words, when I average all the electron energies, one of these orbitals gets spit up high, really high up in energy, right? But there's no electrons there. And so the average energy here will be lower than the average energy here. Does everybody see that? Because in this case, all the orbitals are occupied. Here, we leave the highest energy orbital empty, unoccupied, meaning that the average energy is going to go down. Does that make sense? And so one thing is all nickel 2 complexes are square planar. Well, the same thing holds with platinum. Platinum 2 plus are square planar. Platinum 4 plus are typically octahedral. And so we chose between, based on magnetic properties, nickel 2 complexes are diamagnetic or paramagnetic? They're diamagnetic. And that automatically eliminates the tetrahedral. So that's example 24-5. Experimentally, these are diamagnetic. They must be square planar. Could we similarly use magnetic properties to establish whether the mean complex of nickel 2 is octahedral or tetrahedral? And so let's see the mean complex, octahedral versus tetrahedral, to see if we could use magnetic properties. Are they different, you know? And so nickel 2 plus, octahedral, 1, 2, 3, amine, low spin, 1, 2, 3, 4, 5, 6, 7, 8. This is the octahedral versus the tetrahedral. Tetrahedral, 1, 2, high spin, 3, 4, 5, 6, 7, 8. Could you use magnetic properties to tell the difference between... No, you can't. They both give the same number of unpaired spins. So it's not possible. All right, in both hexa-aqua and hexa-cyano complexes, the iron is present as iron 2. However, the hexa-aqua is paramagnetic, whereas the hexa-cyano is diamagnetic. Explain. And so let's look. Iron 2 is how many electrons? How many d electrons? 6. And so we have iron 2, which is d6. And we have hexa-cyano is what? Strong or weak? Strong. And hexa-aqua is weak. We got 6 electrons. 1, 2, 3. Strong means low spin. 4, 5, 6. Weak means high spin. 1, 2, 3, 4, 5, 6. Which one is paramagnetic? The hexaaqua. Which one's diamagnetic? The hexacyano. All right, and just one more. This is from the advanced section, 83, I think. Of the complex ions hexaaqua and or trisethylene diamine, one has a yellow color, the other blue. Which one would you expect to be yellow? Which one blue? Aqua should be blue.
Strong.
Yeah, aqua's weak.
Or appears strong.
It appears strong, right? Absorbs low, appears high energy. Ethylene diamine's strong, so it absorbs blue, but appears lower, or high, appears low. So that was it for the crystal field theory. Okay. Let's take a break and then we'll start the next section.